Okay, Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Aiman bin Muhammad Shukor, and I will explain for the question 1 for lab 4 DC high voltage generation and measurement. Okay, so we move to the question 1. So the question asks me to rearrange similar picture as shown in figure 1 and figure 2 for parallel DC high voltage measurement using frequency converter and picoscope, and then draw a complete schematic circuit for AC and DC. And finally, you have to take into account the connection of braided copper cable from floor pedestal that holding 100 picofarad secondary unit for AC, and pedestal that hold 280 mega ohm for secondary unit for DC, and suggest the safety rule action. Okay, so this is the figure 1 and the figure 2 we already done in lab 3 for AC high voltage measurement. So now I will show you the arrangement for DC measurement. Okay, so this is the arrangement for DC high voltage measurement. So let me show you the figure. Okay, this one. So basically we will start with the 100 picofarad here. Okay, this is for AC high voltage measurement that we already done in lab 3. Okay, so from here we will use a high voltage diode 100 kilo ohm and 20 milliampere. Okay, so here we use two high voltage diode. Okay, this one the green one. Okay, actually this diode is functioning as a rectifier. Okay, so here the blocking voltage for one unit is 140 kilovolt. So we use two diode, so approximate to 280 kilovolt. Okay, so the connection here is from the connection connection top here. Okay, so we connect and then connect. This one is insulating support. Okay, so at the floor pedestal, the connection here we use space bar. Okay, so actually from this floor pedestal to this floor pedestal we connect to the space bar. Okay, and then until after the second high voltage diode we connect to the smoothing capacitor, and the rated value is 25 nanofarad. So here the function of this capacitor, smoothing capacitor, is to reduce the impulse. Okay, so from here we connect the parallel resistor 2.4k ohm. Okay, here is to reduce the energy charging from this capacitor. Okay, so from this one, from the parallel here, parallel resistor here, and then we connect to the one more insulating support, and then the floor pedestal, and from and as you can see from this picture, here is the grounding switch. Okay, for the other side, for the parallel, okay, so we connect to the measuring resistor 280 mega ohm with the connecting rod and the spacer bar here. Okay, so this one from the floor pedestal here we will connect to the secondary unit. Okay, so as you can see here, for the AC measurement we use AC secondary unit. Okay, for this DC measurement we use DC secondary unit with the rated of 40 ohm. Okay, 14 okay, 14 ohm. Okay, so from the pedestal, floor pedestal that hold measuring resistor 280 mega ohm, we connect to the BNC female to banana connector that connect to the secondary. Okay, so from here the connection is we use coaxial cable. Okay, same with the previous lab, which is the AC measurement. We use BNC female to banana connector and then connect to the secondary unit, and then connect to the BNC female banana connector male, and then okay, this part is we call it BNCT junction. Okay, so here from the BNCT junction, one outlet here we move to the picoscope, okay, for measuring, and then the other one outlet is we connect to the frequency converter at VM3. Okay, for information, VM1 and VM2 is for SC measurement, and then VM3 and above for the DC measurement. So we connect to the VM3 here. Okay, so and then the orange line here is the connection for the copper braided for grounding system. Okay, so this is the arrangement for the DC high voltage measurement. Okay, so next we move to the schematic diagram. Okay, so we will start with the supply here from frequency converter. Okay, and then go to the transformer. Okay, so this schematic will show you both AC and DC measurement. Okay, so here the connection to the first capacitor. Okay, so 100 picofarad here, and then we will go to the high voltage diode. Two high voltage diode we use here. Okay, so here actually we have insulating support here, and then the floor pedestal at the below here. So same goes to here. So and then we connect to the smoothing capacitor. Okay, this is a smoothing capacitor, 25 nanofarad. Okay, and then from here we separate into two. We connect it as parallel. So one we connect to the parallel resistor. Okay, here, and then from the parallel resistor here we connect to the grounding switch, and then we use the cable here, and then to connect the grounding switch at the side cabinet of the frequency converter. Okay, this one for the DC measurement. Okay, after we connect to the, here is a parallel measuring resistor 280 mega ohm. Okay, and then we connect to the secondary unit here. Okay, as you can see here, the purple line here is the coaxial cable. Okay, so we use the coaxial cable attached to the secondary unit, and then here is the BNCT junction. Okay, one we go to the VM3 at the frequency converter side cabinet, and then the other one we connect to the picoscope. Okay, this one is the DC measurement. Okay, so here is the AC measurement. From the first 100 picofarad capacitor here, we connect to the secondary unit here. So actually here is, this is we connect with the coaxial cable. Okay, the coaxial cable here, and then this one is the BNCT junction, and then okay, the purple one we go the purple one is coaxial cable. Okay, for the first junction we connect to the picoscope, and then the second junction we connect to the VM1 at the frequency converter side cabinet. So actually here we can see, or we can obtain both measurement for DC and AC. Okay, so this is for description. Okay, the red line is live, the black one is neutral. Okay, the green one is grounding. Okay, the purple is coaxial cable connection. Okay, and then the orange one is copper braided grounding. Okay, this is for the schematic diagram. Okay, next for copper braided connection. Okay, as you can see here from the during the lab session. Okay, the copper braided need to connect or need to link with both secondary unit. Okay, here is for SC measurement. So the connection of copper braided here need to connect with the floor pedestal that hold 100 picofarad. Okay, and then connect to the secondary unit for SC measurement. Okay, and then we attach to the here is measuring resistor 280 mega ohm for DC measurement. Okay, we need to connect the copper braided to the floor pedestal here, and also the DC secondary unit here. Okay, for advanced safety purpose, all of this floor pedestal we need to connect with the copper braided. Okay, the DC secondary unit, the SC secondary unit, the floor pedestal here, and the grounding switch. Okay, here our grounding switch. So the grounding switch also need to be connected with copper braided for grounding system. Okay, and then other than that, for safety purpose also, here at the grounding switch, we need to make sure the rod need to touch the top electrode of the insulating support. Okay, that's all from me. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Husaini bin Hasni. So today I will present to you about lab 4 section 2. So section 2 will be configuring the procedure of setting the kit control and picoscope. So Roman number 1 will be our source control. So source control will be inside the kit control here. So there is difference of both display. This is picoscope and this is kit control. So source control is located inside the kit control. So what is source control? Source control is the control element for input that will be fed to the primary side of the high voltage transformer. So this is the source control here. We have a higher than symbol here with double and triple, and also lesser than symbol with double and triple symbol here. So in order to control the input to the high voltage transformer, we somehow need to do some setup inside the source control. So basically in kit control, we have two main setup. The other one is unnecessary to do anything, but for customer setup here, we need to declare our increment for each respective symbol here. Okay, so let's say in this case for single one, we want to have an increment of 0.1, and double an increment of 1, and triple an increment of 10 kV for instance. Same goes to the decrement here. So this is the setup that we have, that we need to do for source control here. Okay, okay, that is okay. This is the clear view of the source control here. So for this image here, we don't do anything yet. We do not give any input here, so it indicates 0% here. So that is for source control. And okay, this is the primary side of the transformer progress. Okay, as you can see here, the monitoring for primary side of the transformer is located just below the source control here. We have a source voltage, we have source current, and the graph just below it. Okay, so for this display we don't give any supply yet, so that's why we see 0% here and no any voltage here and current, but somehow we have some noise here, so noise in source voltage and source current. This phenomenon is commonly occurred in high voltage environment. This is common. Okay, so let's say we do an increment of 10% here, 10% for about we click this triple button, we increase 10%. Okay, we increase 10% supply to the high voltage input primary side, so we obtain the source voltage at the primary side right now is 46.74 volts, and the source current is 170.73 milliamps. Okay, and as you can see below here, inside the red circle here, we do see some spikes over here, which indicates graphically the increment of source voltage here. So both of this graphical display and the value here must be tally between both of them. So that is for primary side. That is for primary side. And system monitoring for secondary side with X slots is located here at the right side of both of this display, graphical display. Okay, so we have X slot here, 1 until 8 for slot 1 and slot 2 for VM1, and slot 3 and slot 4 for VM2. So slot 1 until slot 4 for AC measurement, while slot 5 until slot 8 for DC measurement. Okay, for lab 4, in lab 4 we do some DC measurement, so we need to turn on this slot 5 to obtain DC measurement. Okay, so for this display we have some 30% of increment here, so there is a change occurred in source voltage right now, which is 137.96 volt in the primary side with 480.83 milliamp of current, input current. So the output we could observe and measure here, which is around 33.482 kilovolt for AC measurement, and for DC 42.5 volt. It don't show kilovolt, something like that. For DC. This is for 30% of increment for X slot. Basically, X slots is located inside the kit control. The measurement that is being measured in the X slot system can be tally with the measurement in the picoscope. Later on, I will show you the display in the here we could tally the reading here with the picoscope here. Okay, so as you can see here, this is DC measurement here, 42 point something kilovolt, and this is 43.858 kilovolt. So quite difference, but somehow it's almost equal to each other. So this is the differences of monitoring using kit control and picoscope. So next on, we move on to the alarm system. Alarm system is one of the important element inside this high voltage system, because it plays with safety element, the safety of the high voltage equipment itself and the operator inside the field. So basically, alarm system deals with a interlock system. Okay, so in this system we have interlock of emergency button, limit switch at the door, and gate, I think so. So in this display here, over here, the alarm is on because of, we can see here the interlock, which mean the interlock at the door, which indicate that the door is not properly closed. So that's all. That's why the alarm is triggered. And when the alarm is triggered, we could not do the injection to the high voltage transformer. So the next alarm would be emergency button. So when we hit or press the emergency button, it will automatically shut down the power and alarm will be still on. That's why we could not do injection. So in order to do injection, we need to clear both of these fault first. So somehow the operator need to reset the emergency button here and close the door properly. And the next step, the operator need to press the alarm button here, the red alarm button here, and press the reset button here, and the system should turn to green and ready to do injection. So this is the display when there is no alarm occurred in the system. So the system is good to go. Okay, so next, the customer setup in kit control. Okay, customer setup in kit control. Previously we have done setup for source control here. We have done setup for source control up here, the manual step. The next step will be the setup of the calibration area here. So this is one of the most important setup that we need to do before we do injection and measurement. So basically, we in lab 4 we have two secondary equipment. The first one is capacitive secondary equipment to measure AC voltage and voltage, and the second one will be the resistive secondary equipment to measure DC voltage. So inside this calibration area, we need to turn on and key in the value of the divider ratio. Okay, so for this divider ratio, we could obtain it inside the datasheet. So let's say the number one will be the capacitive secondary equipment here. So how do we get this value? We need to refer it to datasheet. So this is the datasheet for the AC output voltage capacitor, secondary capacitor. This secondary capacitor, this is the serial number, and this is the divider ratio value. So we need to key in this value to the area here. Okay, same goes to other. So the next slot will be, we just need to tick it, and for DC measurement we need to tick at slot number 5, because slot number 5 is for DC measurement. And note that we need to properly select this voltage. Okay, we want to measure voltage. We want to measure voltage here. So this is DC, which is resistive secondary equipment. So before we key in the data here, we need to do some check to the datasheet to observe or to check the divider ratio for resistive divider ratio. So how do we obtain it? So this is the DC output voltage measurement, secondary resistor equipment. So this is the serial number, and the divider ratio value would be here, 20414.4 here. So this value we need to key in to the area here, and the voltage must be set here, and the customer setup is complete. So the important section in picoscope when we do measurement, for the case we want to measure the AC measurement, AC voltage, we need to somehow click on this tab. We need to turn on this channel, make sure that the channel is active, and we need to double check the divider ratio that is previously that we have key in inside the customer setup, and we need to ensure that we properly click on the correct side here. For let's say channel A, we measure AC voltage, we click on AC area here. So this is important because if we mistakenly click a wrong tab, we could not obtain a correct measurement, obviously. So this is for DC measurement. So DC measurement in channel B, in picoscope. So we need to click this tab, channel B, and ensure that the channel is active here, and we need to do some observation here. To do some observation, either the divider ratio that we previously key in is still the same, and we need to turn on this channel and tick on the DC area here to obtain the correct measurement. So all of the step is important because to obtain the correct measurement. So that's all I think for section 2. Assalamualaikum warahmatullahi wabarakatuh.
Good day everyone. Today I will cover for section 3. For my part, I will be compare the result for reference speed control and the display microscope DC and the calibration procedure. In this section, our group will show the comparison of the result of VRMS between the reference, which is from the speed control AC, and the display, which is from the microscope DC. From the DC voltage measurement, they will be different in display speed control and display microscope. Before experiment is done, a calibration needs to be done to make sure the output voltage in the percentage can be selected correctly. For the calibration procedure is as below. Firstly, the serial number must be recorded first from the secondary capacitor and must be tallied with the manual book. Secondly, from the serial number obtained, the divider ratio can be determined according to the manual book. For this experiment, lab 4, the divider ratio is 204:14.4. For the third one, at the gate control setting, the alarm need to be turned off first. The interlock switch at the door must be closed circuit, means the door need to be closed for safety purpose. Then the emergency button on the to be released and press the red button for the alarm system. Finally, the reset button on to be pressed to make the alarm button green is in ready condition. And finally, the measuring calibration is set up and go to the customer setup, change the VM1 to according to the divider ratio, which is 20K 414.4 volt. After the calibration is done, the data between reference kit control and display microscope were recorded as table below. As you can see over here, the difference between reference kit AC and display microscope DC. For the range, 10 will be selected as the range. Next, the percentage error for each sample is range of 10% will be calculated by using this formula. Percentage error equal to reference minus display over reference times 100. For the percentage error, as you can see over here, the average percentage error is 30%, and for the first one is negative 76.91. From the table of calibration fact, as you can see, they are using range of 9 instead of 10. From the error, it is less than 1%. From the result of the percentage above, there are major difference between reference voltage, gate control and display voltage. This can be clarified because all of the data from 0% output voltage to 50% has an average percentage value of 13%, which means the error is not acceptable and not the same in the calibration fact from the lab sheet. However, the error will existed in the system that the reason why unstable and inconsistency source of voltage. This is due to the background noise that occurred at the environmental surrounding, that sometimes the noise frequency is at the same level with our system in Malaysia. Standard frequency is 50 Hz system transmission of voltage. For conclusion, we are able to learn how to construct high voltage DC measurement by using kit control and microscope 3000 series. We are able to configure the procedure of setting for FC kit control 4.0 and the microscope. Then we are also able to do discussion and analyzing the comparison of the result from reference and display. The percentage error of the 0% is very caused by the remaining charge that contained in the device after the test has been done, and that's why required to discharge it back after the test has been done. Last but not least, another error that probably can occur is human error during the setup. As we know, this measure about DC 7 VRMS that connected to point VM1, so the coupling setting need to be set up to DC which are not sinusoidal waveform. Thank you.